Welcome back everyone. In this lecture I will continue to prove some more properties of the set of roots. So, indeed we will prove that the set of roots actually will satisfy the properties of the root system. So, let us begin. So, first I will recall what we have done so far. So, we actually fixed a maximal toral subalgebra inside our semi-simple Lie algebra G. So, G is given to be finite dimensional semi-simple Lie algebra over C. So, now with respect to this maximal toral subalgebra and then with respect to the adjoint action of this maximal toral subalgebra on G. So, we can write G as direct sum of these root spaces. So, in particularly, so we have G equal to H direct sum G alpha, alpha is in phi. So, this is the root space decomposition that we have actually proved already. So, in this root space decomposition, recall that G alpha is nothing but those x in G such that the bracket H x is given to be alpha of H x for all H in H. Note that G naught is nothing but H. Okay. So, these are all the things that we have already seen. So, we also proved some of the properties of these roots. So, what are all the properties we proved? We observed that 0 is not in phi and then the span of phi is actually equal to H star, and then if alpha is in phi, so then we proved that minus alpha is also in phi. So, later we have used this information in order to actually get this SL2 triple. So, for alpha is in phi, so we given any non-zero element x alpha inside G alpha. So, we actually constructed this y alpha inside G minus alpha such that this subalgebra generated by this x alpha y alpha that becomes isomorphic to the SL2C. So, that means the span of x alpha y alpha and then this H alpha which is x alpha y alpha bracket. So, this is isomorphic to our SL2C. So, this three dimensional subalgebra we denoted by SL2 of alpha. So, for each alpha, so we have this SL2 triple. So, we will see later that these SL2 triples actually kind of builds that our entire Lie algebra. So, we will use this SL2 triple or this SL2 alpha and then use the representation theory of this SL2 alpha. Then we conclude more about the properties of the root systems and the root spaces. Okay. So, we will naturally make this SL2 alpha act on this G via again adjoint action. So, via adjoint action. So, what is the meaning of that? So, given x in SL2 of alpha, so this x will act on G by sending y to bracket xy. So, that is the action we are talking about. Okay. So, let us look at some interesting submodules of G which are SL2 alpha submodules. Okay. So, the very first submodule that comes to our mind is SL2 alpha itself. So, if we take SL2 of alpha, so recall this is the span of x alpha, y alpha and h alphas being this bracket x alpha, y alpha. So, this is indeed SL2 alpha submodule. So, this is indeed SL2 of alpha submodule. So, what it is actually as SL2 of alpha submodule. So, note that it is naturally isomorphic to the adjoint representation of SL2. So, in particularly if we compute the eigenvalues of H alpha, you can see that H alpha act on x alpha as twice x alpha. Similarly, H alpha acts on H alpha by 0 and H alpha acts on Y alpha by minus 2 Y alpha. So, that means this SL2 of alpha as SL2 of alpha module naturally isomorphic to V of 2 as SL2 module. Okay. So, this is very interesting sub representation of G, SL2 sub representation of G. So, now we will actually construct another interesting sub representation. So, which is again very useful. So, we take this V to be H sum SL2 of alpha. So, this is indeed, if you think about it, so this is actually going to be H direct sum C x alpha direct sum C y alpha. So, it is actually dimension H plus 2 dimensional SL2 of alpha module inside your G. So, why it is actually SL2 of alpha submodule? So, that is easy to check, because if we take x alpha and then apply it on any H, so then we can see that this is going to be minus H x alpha. So, that means this is going to be minus alpha of H x alpha. And similarly, if we compute y alpha on any H, you can see that this is going to be minus bracket H y alpha. So, that is going to give us alpha of H y alpha, and this is true for all H in H. So, now elements of SL2 alpha will be invariant under action of SL2 of alpha, that is very clear. So, that means this V is indeed SL2 of alpha submodule. But if we actually go back to SL2 representation theory, you can see that this is actually finite dimensional SL2 module. So, now in any given finite dimensional SL2 module using Weil's complete reducibility, we can see that any finite dimensional module can be written as a direct sum of irreducible modules. So, in particularly, so recall this the following important fact from SL2 representation theory. If V is finite dimensional SL2 module and V, if you write it as direct sum of V1 etc. Vk, where each Vi's are irreducible. So, then if you want to compute the number of components k inside V, then you can easily see that. So, this will be exactly equal to the dimension of this V0 plus the dimension of V1. So, what is V0? So, V0 is the dose vector V in V such that HV actually kills, and then V1 is nothing but those vectors V in V such that HV acts as identity. So, what is the meaning of that? So, this is eigenspace corresponding to the eigenvalue 0, and this space is eigenspace corresponding to the eigenvalue 1. So, if you compute the irreducible decomposition of this capital V, then we know that this will be written as direct sum of these irreducible modules, and each irreducible module will be isomorphic to some V of di. So, but we know all the H weights of V of di. The H weights are H eigenvalues of this V of di. So, they are all minus di plus di etc. di minus 2 etc. minus di. So, this will differ by 2 and then it will start with di and then end with minus di. Now, depending upon the parity of di, either 0 will be eigenvalue or 1 will be eigenvalue for each Vi, and it is exactly each eigenspaces will be having one dimensional. So, that implies that V of di 0, either this is non-zero or V of di 1 is non-zero. Not only that, in this case either we will have dimension of V of di 0 is 1 or the dimension of V of di 1 is 1. So, that means if you are interested in computing the number of irreducible components that occur in the decomposition of this capital V, so it is enough to just count the number of the dimension of the zeroth eigenspace with respect to H, and then the dimension of the one eigenspace with respect to H. Okay. So, because these dimensions will contribute to each irreducible module inside capital V. So, if we go back to this representation, which is H sum SL2 of alpha, you can see that. So, this representation now can be written as kernel of alpha direct sum this SL2 of alpha. So, now if you think about it, this kernel of alpha, this corresponds to the H eigenvalues, H alpha eigenvalues will be 0. So, because if we take H alpha and then act it on this H, so this will be 0 for all H inside this kernel of alpha. And then if we take this SL2 of alpha, we have already seen that. So, this is irreducible and this corresponds to exactly V of 2. So, this is isomorphic to V of 2 because this is isomorphic to adjoint SL2 representation. So, that means this module, this capital V that we have constructed. Okay. So, this capital V, which is H sum SL2 of alpha, is given by kernel alpha direct sum this SL2 of alpha. So, this kernel alpha corresponds to direct sum of this trivial SL2 modules. So, that means this is exactly equal to V of 0 power direct sum dimension H minus 1 times that V of zeros, because each V of 0 will have one dimensional irreducible module, and then this will be exactly equal to V of 2. So, indeed we get as a SL2 decomposition. So, this module capital V will be V of 2 direct sum this V of 0 exactly dimension H minus 1 times multiplicities. So, this is how you break down this H sum SL2 of alpha. So, now let us use this information and then try to get what root spaces and what multiple of roots can occur. So, let us use this information. So, for that what we will do, we will actually construct another SL2 of alpha module, which we denoted by capital U. So, what is this capital U? Capital U is nothing but you take H and then you take all the sum of this G C alpha, where C is actually non-zero. So, C a priori varies over complex numbers right now, but we will see in a minute that there will be lots of restriction on C. Indeed, we will prove that C can be exactly either plus or minus 1. But before that you can see that this is clearly SL2 of alpha submodule. So, U is SL2 of alpha submodule of G. So, now since this is a finite dimensional module as being a subspace of G, so this is finite dimensional SL2 of alpha module. So, in particularly all the H alpha eigenvalues, so that must be integer. But let us compute what will be the H alpha action. So, H alpha acting on H will be 0 for all H in H, and then if we take H alpha acts on this X will be just so where let us say X is coming from G C alpha, then you can see that H alpha acting on X will be C alpha of H alpha times X. But recall this alpha of H alpha must be 2. So, that means this is going to give us twice C x. Now, since all the H alpha eigenvalues of this U must be integer, so we get this 2 C, they are all integers. So, in particularly we get immediately that C must be of integer. Okay. So, this is the first restriction that we are getting immediately. So, now take this U, since this is a finite dimensional SL2 module. this can be written as direct sum of irreducible modules. So, we would like to see what kind of decomposition it has. So, for that purpose let us write down this U as you can already see that this U contains this H sum SL2 of alpha. So, we know how to decompose this H plus SL2 of alpha. So, that is already written as kernel alpha direct sum this SL2 of alpha. So, let us say we have some more module that are left inside U. So, this is a submodule of U. So, let us say it has a complementary submodule, let us call that is W. Okay. So, W is a complementary SL2 module submodule of this capital U. Okay. So, our ultimate claim will be actually this W must be 0. So, this is what we want to prove. So, let us assume on the contrary this W is not 0. Okay. So, otherwise let us say this W is actually non-zero. So, then what we want to do? We want to analyze what will happen now. Okay. So, note that if we write this U as direct sum of irreducible components, then the number of irreducible components that occur inside this capital U. So, that will be equal to exactly the dimension of this U naught plus dimension of this U 1, where U naught is the 0th eigenspace of H alpha and U 1 is the 1th eigenspace of H alpha. So, this is exactly the number of irreducible components that we know. Okay. So, now if we actually go back and then see what are all the eigen values of H alpha. So, we already see that the H alpha eigen values must be twice C. Okay. So, now let us put them together and then see what really happens. So, note that if we take this capital U, so this capital U is nothing but what? It is H sum direct sum G C alpha, C is non-zero. So, if we just take this U 0 which is the 0th eigenspace. So, that is nothing going to be equal to H, because H is going to be subset of this U 0, because H alpha acts on H by 0 for all H in H. So, that means H is contained in this U 0, and then we can see that whether there is anything left. So, that is if at all, if it comes from, then it should come from this G C alpha. But if you go back and then look at the action of H alpha on this G C alpha for x in this G C alpha, you can see that the bracket H alpha x is nothing but exactly equal to 2 C x. So, if this hexes actually comes from this 0th eigenspace, then that forces that this 2 C is being 0. So, that means C being 0. So, that means there is nothing else that is left in this 0th eigenspace. So, that proves that this U naught must be equal to H. Okay. So, this is something we could observe immediately. So, now you can see that if W is non-zero, so then this W must contain some irreducible representation. Okay, let us call it that is V D. So, which is inside W. So, this is irreducible SL2 representation. So, suppose this D is even. So, then what happens? You can see that the 0th eigenspace of this V D thus must be non-zero. So, V D 0th eigenspace. So, this is the 0th eigenspace, of course, with respect to the H alpha. So, this must be non-zero, but V D of 0 is inside your W 0, but W 0 we just saw that that must be 0, because U 0 is itself H. So, this forces that W 0 must be 0, because W being the complementary of H, because H is actually lies inside this kernel alpha direction SL2 of alpha. So, that forces that this V D 0 must be 0, which is a contradiction. So, this contradiction we got by assuming D is being even. So, that forces D must be odd, okay. D must be odd integer. Okay, before considering this odd integer, let us actually see what we get from this D cannot be this even integer. So, for that let us take this alpha inside phi. Okay. For some reason, let us say twice alpha is also in phi. Okay. If 2 alpha is in phi, okay, for some alpha in phi. So, then what happens? So, if we compute this H alpha eigenvalue for 2 alpha. Okay. So, if 2 alpha is in phi, then just compute 2 alpha of H alpha, you can see that that must be 4. So, but what is U? U is already given to be kernel alpha direct sum SL2 of alpha direct sum this W, but we know how to decompose this kernel alpha direct sum SL2 of alpha. So, this is exactly equal to V of 0, which is dimension H minus 1 times, and then direct sum V of 2. So, that means this eigenvalue 4 that cannot occur inside this kernel alpha direct sum SL2 of alpha. So, that means if this eigenvalue 4 if at all occurs, this has to occur inside W only. Okay. But that cannot happen, we just verified that. So, there is no V D inside W such that D is even. Okay. So, this leads to contradiction. So, that proves that if alpha is in phi, so then we must have 2 alpha is not in phi. Okay. Any even multiple of alpha cannot be again in phi. So, that is what we verified. So, now we go back to D being odd. Okay. Let us say we have V D which is inside W. So, we have assumed that W is being non-zero. So, W must contain some irreducible sub representation that we are calling it V D. So, we already observed that D cannot be even. So, because of that we may get that D is being odd. Okay. So, let us see what contradiction we get in this case. If V D is actually inside W such that D is odd, so then you can see that V D 1. So, this is that 1th eigenspace with respect to H alpha. So, that must be non-zero. So, that forces that. So, this W 1 which is again 1th eigenspace of this H alpha, that must be non-zero. So, in particularly you get some V in W 1 such that when you act H alpha on V, then you should get V. Okay. But the thing is, this W is coming from the complementary of this kernel alpha direct sum SL2 of alpha. So, that means this W, if you write it as direct sum of eigenspaces, so those eigenspaces must correspond to this G C alpha, there is no other eigenspaces. So, that means this V must come from this G C alpha. Okay. So, now C has to be non-zero, otherwise this G 0 will be H which is inside that complementary space. So, then if you compute H alpha V, then you can see that this is given by C times alpha of H alpha times V, which is exactly equal to 2 C V. But that forces that 2 C must be equal to 1, that forces that C must be equal to off. Okay. So, that means we got that of alpha is in phi. But note that already alpha is there in phi, which is twice of alpha. So, this is already in phi, but this is a contradiction. We just proved above that for any alpha in phi 2 alpha cannot be in phi. So, that means of alpha also cannot be in phi. Okay. So, that proves that D cannot be odd as well. Okay. Since D cannot be even as well as odd, so there is no option for D. So, that proves that W must be 0. So, this forces W must be 0, there is no other option. Okay. So, that means the U that we constructed, which is H sum direct sum G C alpha C non-zero, is exactly equal to the kernel alpha direct sum SL2 of alpha. So, this indeed actually gives lots of striking facts. You can see that G C alpha is non-zero, then that would imply immediately that C is actually either plus or minus 1, and then G alpha is spanned by C x alpha, and then G minus alpha is spanned by C y alpha. Okay. So, that means the dimension of G alpha is 1 for all alpha in phi. So, that is what it proves. And not only that, if alpha is in phi and C alpha is in phi for any C non-zero complex number, then we get C must be either plus or minus 1. So, this is also something we proved using this. So, this puts lots of restriction on the root spaces. So, now we are ready to prove some more properties of this root system, which are again very important. So, for that purpose we need to consider what is called this alpha string through beta. Okay. So, this is something that we want to consider. For that purpose, let us actually define what is called this alpha string through beta. Okay. So, let us say alpha beta both are elements of phi. So far what we have actually observed, we just looked at one particular root and then looked at its multiple of alphas, and then we concluded something about the root spaces and so on. But now what we want to do, we want to understand how two different roots alpha and beta they actually interact with each other. So, you take alpha beta is in phi such that this beta is actually not equal to plus or minus alpha. If it is plus or minus alpha, we know how to deal with that. So, because of that we just assume it is not plus or minus alpha. So, then what we do, we consider what is called this alpha string through beta. Okay, this alpha string through beta. So, what it is? It is by definition, maybe we just denote it by S of beta comma alpha. So, this is those beta plus k alpha such that okay, you choose those k inside integer such that these beta k alpha they are all roots again. Okay. So, this is what we call alpha string through beta. So, we want to actually conclude many things about this alpha string through beta. So, for that purpose what we will do, we will actually consider this again another SL2 of alpha module. So, there is this natural module, let us call it M. So, which is just the direct sum of all this G beta plus k alpha, where k now comes from Ez. Note that if k does not come from this S beta of alpha, then G beta plus k alpha will be 0. Okay. K is not from S of beta comma alpha. So, then we get G beta plus k alpha equal to 0. Okay. So, and note that since G itself is finite dimensional, so this S of beta alpha must be finite. So, that means there exists some large q such that beta plus q alpha is root, and there exists R such that beta minus R alpha is also root. Okay. So, since S of beta alpha is finite, so we can find q and R both are non-negative integers such that beta plus q alpha. So, this is inside your S of beta of alpha and beta minus r alpha. This is also inside your S of beta of alpha. So, such q and r can be found because S of beta alpha is finite. Okay. So, indeed what we want to climb. So, let me just tell you, I do not want to keep you in surprise. So, the climb is, if we take this S of beta of alpha, we will prove that it is indeed unbroken and it is going to be exactly equal to beta plus q alpha comma etcetera beta plus q minus 1 alpha etcetera beta etcetera beta minus r alpha. So, it will go all the way down to beta minus r alpha from starting from beta plus q alpha. So, this chain is in some sense unbroken and then it will start with beta plus q alpha and end with beta minus r alpha. So, it is like the interval bracket q minus r, okay, it is unbroken interval. So, let us prove this. So, for this purpose we need to understand the structure of SL2 module, this M. Okay. Note that if we take this M, so then let us compute all the H alpha eigenvalues. So, for x inside G beta k alpha, we can see that H alpha x will be exactly equal to beta plus k alpha of H alpha times x. So, that means exactly beta of H alpha plus twice alpha, sorry, twice k times x. So, that is what we get as eigenvalues. So, beta of H alpha plus 2 k. So, these are all the eigenvalues of this of this M. So, since this M is finite dimensional SL2 module, so we can immediately get that this beta of H alpha plus 2 k, they must be actually integers. In particularly for k equal to 0, we get beta of H alpha must be integer, because for k equal to 0, G beta is sits inside M. Okay. So, this is something immediate. So, now what we will do, we will just try to understand the SL2 alpha module structure of this direct sum of G beta plus k alpha, where k runs over integer. So, note that the dimension of this G beta plus k alpha, they are all 1. Okay. So, because dimension of G alpha is 1 for all alpha in phi. So, in particularly if it actually survives, if G beta plus k alpha, if it is non-zero, so then we can easily conclude the dimension of G beta plus k alpha must be 1. So, now if this is 1, then what happens? You can see that the eigenvalues are of the form beta of H alpha plus 2 k. So, that means the parity of this beta of H alpha and whatever eigenvalues that survive, they have same parity. So, if beta of H alpha is even, then all the eigenvalues that survive here, they must be even. Again beta of H alpha is odd, then the whatever eigenvalues that survive, they are all odd. So, since this eigenvalues are all same parity, so that says that either M of 0 will be non-zero or M of 1 will be non-zero. Since all these eigenvalues differ by 2 or this differ by multiple of 2, and all these root spaces, they have one dimension, that forces that either we will have the dimension of M0 is 1 or the dimension of M1 is 1. So, that means this M that we have is indeed actually irreducible module. it is irreducible SL2 module. So, in particularly this will be isomorphic to some VD. So, now note that we already know what are all the H alpha eigenvalues of this VD. So, that is nothing but starting with D, D minus 2 and so on up to D minus D plus 2 and then minus D. So, this must be exactly equal to, so if we take beta of H alpha plus 2k, where this beta plus k alpha comes from S of beta of alpha. Okay. So, this is exactly what we have. Since they all differ by multiple of 2, you can see that. So, if we take this q and r as above, so whatever we have fixed this q and r, from that you can see that. So, if it is starting with that q, then we will get beta of H alpha plus 2 q and then it will go. So, you just subtract by 2 because every time you are subtracting by 2. So, this is the max value. So, beta of H alpha plus 2 q minus 1 and so on. Then you go all the way down to minus beta of H alpha minus twice r, and this is going to be your minus d and this is going to be your plus d. So, that gives us the following relation. So, beta of H alpha plus 2 q must be equal to minus beta of H alpha plus 2 r. So, this forces that beta of H alpha is equal to r minus q. Okay. So, we have plenty of consequences from what we have observed. So, beta of H alpha is r minus q and this root string alpha string through beta. So, that is unbroken and so exactly we get all these roots here. So, let me just write down all the consequences. So, if we take, so we just observe that there exist q and r inside Z plus such that beta plus q alpha and so on beta minus r alpha. So, this is unbroken, this is unbroken chain and this is all subset of phi. And the second thing that we observed, beta of H alpha is nothing but r minus q. Now, note that if we compute this beta minus beta of H alpha alpha, so this is going to be exactly beta minus r minus q alpha. So, which is exactly going to be beta minus q plus q minus r times alpha. So, but what is about this q minus r? You can see that this can be at most q and then at least r, at least minus r. So, that implies this beta minus beta of H alpha alpha. So, this is again element of phi. So, this is again very important consequence. So, we have made many interesting consequences. So, let me list all of them. Okay. So, here is the properties of the roots. So, what are all the properties? The very first property that we have seen, the dimension of G alpha, that should be 1 for all alpha in phi. So, that is about the Lie algebra. But anyway, so we also have some other properties like 0 is not in phi and then the span of phi is equal to H star. So, these are also there, let me denote it by 0. And the second property, if alpha is in phi and then C alpha is in phi for C non-zero, so then we must have C equal to plus or minus 1. So, this is there. The third property, you can see that this, if we take alpha beta is in phi, then if you look at this beta minus beta of H alpha alpha, so then that is also must be again inside your phi. The fourth property, if alpha beta is in phi and alpha plus beta. So, this is in phi. So, then that will imply the bracket G alpha G beta. So, this must be non-zero, which is exactly equal to G alpha plus beta. So, let us prove this. So, this G alpha and G beta, if this is non-zero, then that would force immediately G alpha G beta, the bracket must be equal to G alpha plus beta, as the dimension of G alpha plus beta can be at most 1. Okay. So, that is how we can see. So, but why this the bracket G alpha G beta must be non-zero? Again you go back to that irreducible module, that M that we have constructed. So, this is going to be direct sum G beta plus K alpha, where K coming from Z. So, this is the irreducible SL2 module. So, that is we already observed. So, now for some reason, if this G alpha G beta is 0, if G alpha G beta, the bracket, if this is 0, so then what happens, this X alpha, so that is going to kill this X beta. Okay. So, this X alpha X beta, they are all coming from G alpha G beta respectively. So, that means this H alpha is already going to give us on X beta, it is going to give us beta of H alpha X beta. So, that thing makes it X beta as maximal vector. So, maximal vector inside your M with eigenvalue, that is H alpha eigenvalue beta of H alpha. So, that means this M will be spanned by X beta, and then you just apply only Y alpha X beta and so on, and then you can apply up to Y alpha power R times X beta. So, this span must be equal to M, because M is generated by this maximal vector and this becomes maximal vector because M is irreducible. So, M has to be exactly span of these elements. But then look at all the weights. So, this will have beta and then this will have beta minus alpha and so on, then you will have beta minus R alpha. But if you go back, what the assumption, our assumption is alpha plus beta is also a root. So, but it says that these are all the only roots, because this M is nothing but direct sum of G beta plus K alpha, where K is coming from Z. This entire space is becoming span of this. So, that means these are all the only roots in phi, that implies beta plus alpha is not a root. So, which is a contradiction, because we are given that this alpha plus beta or beta plus alpha is a root. So, that forces that this G alpha G beta, so that must be non-zero, since G alpha plus beta is one dimensional and this is a non-zero subspace of G alpha plus beta, that forces that these two should be equal. Okay, this proves most of the properties of this set of roots. So, I will just end with one last property, again that is immediate actually from the properties of the roots. Okay. So, here is the last property. So, G as a Lie algebra generated by G alpha alpha in phi. Okay. We already know that G is actually equal to H direct sum G alpha alpha in phi. So, that means we need to prove that if we call this is G plus, so then this H must lie inside G plus. Okay. So, it is enough to prove. So, it is enough to prove that H is inside G plus. So, how do you one proves that? So, we just take all these G alphas and then see what happens. Okay. For alpha in phi, you know that the bracket G alpha G minus alpha. So, this is going to be this one dimensional space C T alpha, which is same as C H alpha. So, this is going to lie inside G plus, okay, and this is true for all alpha in phi. So, that forces that summation C T alpha alpha in phi. So, this is going to be a subspace of G plus, but note that phi actually spans H star. So, and there is this identification of H with H star via the killing form, So, that means this space must be equal to H. So, H is contained in G plus, that forces that G plus is equal to G. So, as a Lie algebra, these G alphas they also generate this entire G. So, more or less we have proved all the important properties of roots. So, again it is all happening now inside the maximal toral subalgebra, which is defined over the complex numbers. So, somehow we need to actually bring down everything over reals. Okay. So, that is something I will do it in the next class. I will stop now. Thank you.